In this video, we're going to talk about factorial ANOVA, also called two-way ANOVA. On this first screen, I'm just going to set out a basic example that we're going to use for the rest of the video. In a two-way ANOVA, you have two independent variables. Another word for an independent variable is a factor. So in this case, we have factor A, or the first independent variable, which is the testing condition. And then we have two levels of testing condition, which is classroom or beach. So what that means is we have some people who are going to be tested on material that they previously learned in an actual classroom, and other people who are going to be tested on material that they previously learned on a beach. The second factor, or the second independent variable, is the learning condition. Where did these people actually learn the things that they're later going to be tested on? Half of these people are going to be learning in a classroom, and half of them are going to be learning on a beach. This is a table, and then the numbers inside of here are cell means. So this number right here, 16, is a cell mean. And what that represents, that is the average score of all the individuals who learned in a classroom and then later were tested in a classroom. So that's the 16 is the average score of everyone in that combination of conditions. 4 is the average score of everybody who learned in a classroom and were tested on a beach. And the average score of everybody who was learning on a beach and tested in a classroom was also 4. And then finally, the last cell mean is 18. People who learned on a beach learned on the beach and were tested on the beach. Now this number over here on the right is called the marginal mean. That is the average of everybody who learned in a classroom. So you're collapsing across these two conditions because what's common across these two conditions is that everybody in both of these conditions learned in a classroom. And so if we take the average of the cell mean and the average of this cell mean, we'll get 10. Really what you're doing is you're taking the average of everyone who took those, who was in the learning classroom condition. If you have an equal number of people in this condition and an equal number of people in this condition, then what you could do is just take the average of these two means, and it'll give you the right answer. So this means that on average, on average, the number of things people recalled, the number of things they remembered during testing, their score, their DV, their average score was 10. I should have mentioned that the dependent variable, these numbers represent the average number of things that people recalled, their score on the test. How many things did they remember? Okay, and 11 is another marginal mean. 10 is another marginal mean, and 11 is another marginal mean. So 11 is the average of these. This 10 is the average of these. This 11 is the average of these. Now, I'm going to show you the actual raw data so everything is clear here. There were, in this condition, 5 people. Each of these are their scores. 1, 2, 3, 4, 5. Those are the 5 scores of people who were tested in a classroom and learned in a classroom. So that's those 5 raw scores. If you average them, that's where that 16 comes from right there. And then, of course, we can do that for all the other cells. So These are the 5 scores for the people who were tested in a room but learned on the beach. So tested on a room but learned at a beach. So the average of these is going to be 4. And I can do that for the other 2 cells. Now, one of the advantages of a two-way ANOVA is it allows you to make 3 tests with one analysis. So any factorial ANOVA will, with 2 independent variables, because you can have some with more independent variables, we won't go into that stuff, but a two-way ANOVA with 2 independent variables is going to give you 3 significance tests. The first test is, in this case, is the main effect of IV1, the main effect of the IV1 of factor A. In this case, it's the main effect of testing. And what it's comparing is the difference between this 10 and this 11. We're going to do a significance test, and it's going to tell us whether the difference between this 10 and this 11 is likely or unlikely to be due to sampling error. So just like we've done before, we'll go through some computations, we'll come up with an obtained F value, we'll compare that to a critical value, and if the obtained F value is greater than the critical value, then we're going to reject the null, and we're going to say that these 2 means this difference of 1 is unlikely to be due to sampling error if the obtained F is larger than the critical F. We'll have to see. So again, the first test is comparing the difference between these 2 to see if that's likely or unlikely to be due to sampling error. The second test is going to compare the other marginal means. It's going to compare these 2 marginal means to see if this difference is likely or unlikely to be due to sampling error. And then finally, the interaction. Now, what makes the factorial ANOVA so important and so useful in research purposes is the fact that it allows you to test for what's called the interaction between factor A and factor B. In real-world situations, things are rarely as simple as there's only one factor that influences people's response. It's usually a multitude of factors. And that's what the interaction allows us to do. We can test how, in this case, learning condition interacts with testing condition. Now, what the interaction is actually testing is the difference between cell means. So if we look at the cell mean on the pairs of cell means on a given row, we have 16 and 4. What's the difference between those 2? If we take 16 minus 4, we're going to get 12. That 12 is called a simple effect. Now we want to do the same thing for the row under that. We have to do it in the same order, so it's 4 minus 18, and that gives us negative 14. That's the other simple effect. So this 2 by 2 has a pair of simple effects there. And the interaction is testing to see if this 12 and this negative 14 are significantly different. Are they far enough apart that that difference is unlikely to be due to sampling error? Well, it certainly sounds like they're very far apart, but we'll need to do a significance test, right? Because those scores are 26 units apart. So it sounds like these are unlikely to be due, the interaction is unlikely to be due to sampling error. If we look back at the main effects, they're each different by 1. This is different by 1, and this is different by 1. So that seems that it might be possible that that these main effect differences are different due to sampling error. We'll have to do the test to find out for sure. To summarize, the key point here to remember is that when you're looking at main effects, either main effect, that's comparing marginal means. That's the main effect of A right there, comparing those marginal means. The main effect of B is comparing those marginal means. And then the interaction, you have to look inside. You have to use cell means, and you're looking at the difference between cell means. So you're looking at the simple effects. 12 and negative 14. The interaction is comparing the difference between those two numbers. All right, now I'm going to redraw the data from the previous screen. And now the question that we're going to focus on is, how do you enter all of this data into SPSS? Now, a factorial ANOVA is pretty computationally intense. It takes a while to do it if you're going to do it all by hand. Most of the time, we're going to use a computer to do this. Researchers use computers all the time. Rarely are they ever going to do this by hand. So it's pretty important that you know how to enter this data into SPSS correctly. You're going to have 3 columns of data in this situation. You're going to have one column for IV1. This is IV1. And then you're going to have one column for IV2. That's going to be IV2. And then you're going to have one column for the DV, or their score. How many things, DV. How many things did they actually remember? And what we need to do is come up with a coding system. In this situation, I'm going to say that testing, of course, is the first IV. It has 2 levels. I'm going to say that a 1 indicates that they were tested in a room, and a 2 indicates that they were tested on a beach. And learning is going to be the same thing. Under the learning column, a 1 is going to indicate that they were learning in a room, and a 2 is going to indicate that they were learning on a beach. So I'm first going to talk about how to enter this first bunch of numbers, this first line of numbers up there. Well, the person, this is the first person. We'll call him Bob. Okay, his score was 15. So there's 3 bits of information we need about Bob. He was in a room when tested, and he was in a room when he learned. So he has a 1 under the testing column, and he has a 1 under the learning column, and his score is going to be a 15. So we have to put a 1 under testing. Again, we're using this coding scheme because he was testing in a room. He learned in a room, so he gets a 1 under both of those columns. And then we enter his score. And now we have these other 4 numbers to enter. Well, they were also tested in a room and learned in a room. So really, we can put 4 more 1s under testing, 4 more 1s under learning, and then we can enter their scores. And now we need to do the same thing for the second row here. The second row of data, they were still tested in a room, so they're going to get 1s under room, but they learned on a beach, so they're going to get 2s under learning, and then we'll put their scores. So we have a 1 under testing for the next 5 scores, a 2 under learning for the next 5 scores, and then we put the next 5 scores under the score. So now we've just entered this row of data. Now we have to do the third row. Well, the third row was tested on a beach, so they're going to get a 2 under the testing column, and they're going to get a 1 under the learning column. And then we're going to have their scores. So the next score would be 5. And then we would have 2, 1, 8, 2, 1, 1. I'm just going over and finishing up those. And then the last set of numbers is going to be tested on a beach, so they would get a 2. And they were learning on a beach, so they would get a 2. And then we would get their scores. So it would be 2, 2, 22, 2, 2, 15, and so on. That's how you enter data in the factorial ANOVA situation into SPSS. Now we're going to talk about how you would create graphs for the main effects and the interactions of this factorial ANOVA. And here I'm just recreating the same data that you saw on the very first screen. the cell means and the marginal means. Again, the numbers inside the cells are cell means. Numbers out here on the margins are called marginal means. And the first thing I'm going to do is I'm going to graph the main effect of testing. And so I've created a little graph over here. The IV always goes on the bottom axis down here. So I label it, I'm talking about the IV of testing, so I have testing there. And then I have the two levels of testing listed. So there's class and there's beach, 1 and 2 respectively. The vertical axis over here is always the dependent variable, their memory score. How well did they do on the test? Now, the main effect is always going to be dealing with marginal means. And this is the main effect of testing, so we have to use the ones on the bottom, right? These. And so for class, we're going to graph a 10, and for beach, we're going to graph an 11. So there is over class a bar that goes up to 10, and there over beach there's a bar that goes up to 11. That is how you would graph the main effect of testing. Now we're going to do the interaction. Now again, the interaction is using these means in the middle. We have to graph the cell means. So the first thing we do is we generate our horizontal and vertical axes. Again, the horizontal axis, the one down here, is still an IV. You can pick one. I just did the same one I did before. So it's testing with the two levels, class and beach. And the vertical axis is still the dependent variable. But now I need to create a coding scheme. And so this is what I've done here. The other independent variable was learning. And I'm going to use a circle to indicate that people learned in a classroom. And I'm going to use an X to indicate that people learned on the beach. So the first thing I'm going to do is graph the two scores for testing under classroom. So these two scores. I'm going to graph a 16 because they learned in a classroom, I'm going to use a circle. I'm going to graph a 4, and because they learned on a beach, I'm going to use an X. And then I'm going to graph these two numbers using the same circle or X coding system. So here I've done that. The 18 learned on the beach, so they get an X, and the 4 learned on the classroom, in the classroom, and so they get a circle. And the next thing I do is I connect like symbols. So I draw a line from X to X and from circle to circle, and now I've just graphed the interaction. Now, what you're looking for with an interaction is you're trying to see if the lines are not parallel. If the lines are not parallel, you might have an interaction. And the reason why you graph is it helps you sort of explain what the pattern of the data is. So for example, if you were tested in a classroom, which condition of learning is best? If you were tested in a classroom, then learning is best in a classroom. If you were tested on the beach, which condition of learning is best? Beach, because it's higher. So this graph just sort of helps you visualize what's going on. Okay, we have one last screen to go through, and that's the two-way ANOVA source table. This is very similar to the source table you've seen before when we did a one-way ANOVA. This is just going to be a little more complicated because we have 3 effects. In a normal one-way ANOVA, we just had one independent variable. But here we have 3 independent variables. The first independent variable of testing, the second one of learning, and the third is not really an independent variable per se, but it's the interaction of the two independent variables. So we have three tests, right? Just like we started with. We have the main effect of testing, the main effect of learning, and we have the interaction of testing and learning. And then we have error, and then we have total. Well, in order to know if the main effect of testing was significant, or another way of saying that, if the difference between testing on the beach and testing in the classroom, if that difference was due to sampling error, was likely due to sampling error or not, we need to look at this F value. Across from testing, we look at the F value. And that F value is 0.55. We would compare that to the critical value, and the way we would find the critical value is we would take 1 and 16, and we would look that up in the back of the book. Under an alpha value of 0.05, always assume that we're going to use an alpha value of 0.05 unless you are told differently. We would look that up. 1 would give you the column, 16 would give you the row, and then you would find a critical value there. Now, I know that this 0.15 or 0.55 is not going to be greater than a critical value, because if the null is true, you should get a 1. And if the null is not true, you should get a number that's quite a bit larger than 1. And this isn't, so I don't even really need to look it up. I can tell that this is not going to be significant. So the main effect of testing, comparing the numbers 10 and 11 from the first screen, we know that was probably due to sampling error. This is the effect size, and that tells you that this was a very small effect, which makes sense. We do the same thing for learning. Here is the F value. Now in this case, this F value and this F value came out to be the exact same numbers. That does not have to be the case. It just did in this case. So again, we know that the main effect of learning is not significant. And now we need to look at the interaction. Well, we have an F for the interaction of 92. That's huge. It's a very large effect. We would need to look up with 1 and 16 to find the critical value in the back of the book. Again, column 1, row 16 would give us the critical value, an alpha value of 0.05. And again, this 92 is going to be larger than that. So we would have a drawing like this. The F value. And we're going to have the critical value here. And this 92.6 is going to be way out here. So we are going to reject the null. That means that we do have a significant interaction. And then what we would do is we would go back and we would look at the pattern, and we would need to describe that pattern. And that's what I did on the previous screen with that graph, right? If you were tested on the beach, you were better off if you also learned on the beach. And then the opposite is true. If you were tested in a classroom, you were better off if you were actually learned in a classroom. And that would be the interaction. And we'll talk a little bit more about how to describe interactions and how to write them up in a future activity.